Hello, thank you for having such an opportunity. My name is Ritsuki Morohoshi, a PhD student from the University of Tokyo, Japan. My presentation is about the stress field dependency of the Martensitic transformation in Metastable Austenitic steel. This is a list of contents. And first, the social background is given. Japan aims to having 50,000 cubic meter of liquefied hydrogen storage tank will be operated by 2030 to achieve the carbon neutrality by 2050. So the shape of the tank must be converted from the high pressure spherical shape into the flat bottom atmospheric cylindrical shape. That makes the additional material requirements as needed, which is about the seismic resistance around the area at the liquefied hydrogen temperature. And our ultimate goal is to doing this evaluation. However, we couldn't finish it yet. So, and we see that the steel with having the transformation-induced plasticity is a good candidate for this project. However, there's a big problem, which is about we couldn't understand the behavior of the trips around the crack tips. That means that the standard like STM could not guarantee the size independency of the fracture toughness. So obviously it's a big problem. And for example, there are 4 major previous studies investigating about the stress field dependency of the Martensitic transformation. Especially in the data around high stress structurality, which is similar to this fact that it's contradicted to each other. So yeah, so we need to choose the most precise way to measure the stress field dependency of the Martensitic transformation. So eventually, finally, we chose the in situ SEM EBSD tensor test will be the best one because the highest spatial resolution and the low price are indispensable to doing multiple experiments and theorizing the dependency. And next is about the experimental procedures. This slide is about the material and the facilities. We use the 301L austenitic stainless steel because this is the metastable austenitic stainless steel at the room temperature. And this is the tensiler. And the specimen are set here, and the specimen is set, the tensiler is set into the SEM, like the schematic images. So as you can imagine that making the tensiler and conducting the experiment is pretty complicated, but we can do it with a much low running cost. So it's obviously the beneficial point. And this is the specimen that we use. So we arrange 3 kinds of the specimen, each having a different stress structurality, 0.5, 0.0, and 0.33. We call each specimen as the notch specimen, shear specimen, and uniaxial one. And next is about the result and discussion. First, this is the result in the notch specimen. The loading direction is horizontally. And as you can see that the upper one is the SEM, and the lower left is face map, and the lower right is FEM. The next is about the shear one. It's pretty visible that the Martensitic transformation happens as it is loaded, and the wrinkles because of the trips can be observed. And the last is about the uniaxial one. Yeah, pretty visible. And as you can see that the Martensitic transformation happens as it is loaded. However, with this raw forms, we couldn't analyze anything about the quantitative analysis because, so for example, this is the overlay of the green boundaries of the notch test. The black line is showing the EBSD at the 105 Newton, and the red one is at 115 Newtons. From the naked eye, there are the 2 stuffs can be observed easily. The one thing is that red lines are stretched most horizontally, and then we could identify which grains correspond to the grains on the another load. However, obviously it's impossible to manually level all the correspondences. So we need a kind of automation to detect the deformation of the grains. So I make a kind of the system to detect the deformation of the grains. Probably, as you know, that the most famous way to detect the deformation of the grain is the digital image correlation. So let me briefly introduce the comparison between. The main disadvantage the DAC is that we need to spray something on surface. So that makes interfere with the EBSD pattern. Sure it is. However, then on the other hand, the spatial resolution of the triple point matching will be much costlier than the DIC, obviously, because the patterns are much closer. And let me introduce much more about the post-processing process. And this is the triple point. We identified all the triple points at each load, and we identified which triple point is correspond to which triple point on another load in a way that I omitted because the time is limited. But anyway, by doing that, we could identify the deformation of each triple points, and then we regress the deformation of the triple point into any coordinate, assuming the affinity. I mean the linear regression. So next slide showing that affinity regression is enough or not. These are the movies about the overlay of the grain boundaries. If the affinity regression is precisely enough, the original coordinate at any grains at any load can be calculated through the inverse of the accumulated affine transformation matrices. And these are the movies about after applying it. And in other words, that the grain keeps stationary after applying it if the affine regression is enough. So yeah, seemingly that's enough. And this is the typical example of how the grain tracking goes. These are the subgraph of the grains, or as shown in the right one. So we could identify the transition of the every grains and how when it is transformed into the martensite. And the clip with red grain boundaries is the kind of the artificial EBSD showing the where the austenite is just before the martensitic transformation. By doing a lot of stuff, as I said, so finally, we could identify the effective strain by calculating the deformation, because we represent the deformation as a single linear function, so we could represent the single effective strain. So finally, we could compare the previous studies with our own. However, our data when the stress structurality is about 0.5 is contradicted by any previous data. So we are in the process of doing much more experiment and to validate which is correct, mine or others. And as a side note, and this is the result showing where it is transformed easily. And the black line showing the initial grain boundaries, and the red one is the initial austenite. The pink one is the remaining austenite at last. The other color showing when it is transformed. Yes, it's a factory show where it is transformed early. However, there's no visible reasoning behind it. We could say that at least the martensitic transformation can happen from the grain boundaries, but this is the only stuff that I could say. And this is a shell one. And obviously the austenite is much stable. This is the uniaxial one. And in the first place, there was martensitic transformation dependent on stress field. So I made two assumptions. The first is the stress field dependency means this criterion is inaccurate somewhere. So maybe Schmidt factor plays some roles. And the second is that stability of the austenite with different grain size might be different with stress field. So this is the slide about the Schmidt factor. We believe that there's two ways to represent the Schmidt factor. The first way is that the Schmidt factor of the Austenitic at before loading. The second way is that the Schmidt factor of the Austenitic right before the transformation. So these are the result. The x-axis showing the Schmidt factor and the y-axis showing the amount of the newly made Martensite. And the color bar showing the when it is transformed into the Martensite. And at least I could say that the lower one is much more reliable because the neighboring birds doesn't change abruptly. So, and the trend is like that. And this is all the result with different structurality. However, they indicate all the same trends, which means that Schmidt factor is not the answer to stress field dependency of the Martensitic stability. So next is about this grain size. And in two cases, the x-axis showing the initial grain diameter and the y-axis is the amount of the newly made Martensite. So on two cases, as initial grain diameter increases, the newly made Martensite increases. However, only in the share case that it didn't goes like that. So maybe this happened kind of the suppression to leads to the overall the multistatic transformation. We think so, but it's just a kind of assumption. So we need to do a much more experiment to ensure that. So this is a conclusion. Thank you.
Thank you very much.